Hey guys, this is Unit 2, Section 1, Part 3. So we are continuing our talk about pressure, and today we're going to add a little something else to the mix to discuss. So first I want to propose a question. Why does your coffee stay in its cup? So most of the coffee is in the cup, but you know some of it escapes. That's how you smell it. If you think that aroma smells delicious, that's because literally some of the coffee left the cup and got to your nose. So why doesn't it all leave the cup? So the answer is differences in density. What is density? All right. Also, you need to notice that density has a specific symbol. So it looks like this. It's kind of a weird looking key. So if I were to draw the symbol for density, start down here and go around and like that. That's the symbol for density. Now you might ask, why not just use a D? But the reason we don't use a D is that it can be confusing because D stands for distance. And when we have on the x-axis, like how far do you travel in your car, that would be distance. So we don't use a D, we use this funky, it looks kind of like a P. It's called rho, it's a Greek symbol. So density refers to how close or how far apart molecules are. So let's show it in a picture. First, let's think about what the difference in density is. The density of air, so see how we have this funky symbol again? That's the density, and we use subscripts or below to describe what density we're talking about. Density of air is 1.29 kilograms per meter squared, which means if you take a full meter squared of air and then you measure the mass, it's 1.29 kilograms. Versus water, and I'm using water in coffee because you're going to use that a lot in practice problems, and coffee is mostly water. Water has a density of 1,000 kilograms per meter squared, which is why it's so heavy. If you have a big thing of water, it quickly gets really heavy because it's super dense. So if you look at this picture that I kind of sketched out, so it's not exactly to scale, but if we were to draw the molecules of coffee, they might look like this, versus the molecules of air, look how far apart they are. Because this has so much density in the coffee, gravity's pulling down on it, and that's why it stays down so much. So higher density in the coffee, lower density up in the air. Okay, but even if the densities are different, there's something you need to know. Where the two fluids meet, so at this interface right here, there is the same pressure. Now keep in mind when I say two fluids, I could be talking about a gas or a liquid. Both are fluids because both flow. So just in general, so I'm talking the pressure literally right here and the pressure right here. So make sure you draw that in. So molecules in nature don't have a perfectly straight line. So they might do a little jaggedness. So this might be the top items here have the same pressure as the bottom items, but at the same point, it's going to be the same. So pressure can't change abruptly across an interface. So where they change, they have to be the exact same pressure right above and right below that interface. So pressure 1 here is the same as pressure 2. So if we have 3 fluids in a row, what do we know about their densities? So we're going back to that funky symbol. So densities, not pressure, how closely packed the molecules are. So I have the density of air, the density of oil, and the density of water. So you always know that the least dense is on the top, the most dense is on the bottom. So if we were to order these from least to most, it would be the pressure, or the density, I'm sorry, of air, the density of oil, and the density of water. This one is the greatest density. This one is the least dense. So on the top always has the least dense substance. But what do we know about the pressures? Well, we don't know stuff about the pressures in the middle right now, but we do know a little something about these pressures. So right where those things connect. So P1 is the pressure at the very bottom of our sample of air. P2 is the pressure the very tip top of the oil. P3 is going to be the pressure at the very bottom of the oil, and P4 is the pressure at the very top of the water. So remember that at the interface, or where they connect, they have to be the same. So P1 is exactly the same as P2. We also know that P3 is the same as P4, but P2 and P3 are not the same because they're at 2 different points. So I like to think about this in terms of blankets. So when you sleep, you might have some blankets on top of you. The more blankets you have, the more pressure you feel on your body, right? Because the thicker the blankets. So same thing, there's going to be a different pressure here because it's got all this stuff on top of it, versus right here it doesn't have as much pressure because you only have the air on top of it. So pressure depends on depth. Pressure in a fluid depends on depth. If you look at this cup with the 3 holes in it, and water is coming out of all 3 points, and then you can look at these arrows, and the arrows have to do with how much pressure is pushing the water out. You notice at the very bottom, you have the most pressure because you have the most stuff pulling down from its weight at that exit point. The hole at the bottom is going to have the most pressure. So, another question, why is your blood pressure taken at the top of your arm? Well, when you take your blood pressure, you're trying to figure out how well your heart's working. It's the most important part. So, it's at the same height as your heart. It goes straight across. So you take your blood pressure at the top of your arm. So that way it's at the same point so you can see what the pressure is on your heart. All right, if you move down the depth H into a fluid and it has a specific density, then the pressure is going to increase by this formula. So this is how much your pressure increases every bit you go down in a fluid. Remember that 9.8 meters per second squared, that is G, or your gravity on Earth. So you take density times gravity times height. Make sure the density is whatever fluid you're in. All right, so the change in pressure is going to be whatever the density is times gravity times height. So let's do a practice problem. Motor oil has a density of 900 kilograms per meter square or meter cubed. So if you have a storage tank that's filled with motor oil, so we're pretending that this is our storage tank, what is the difference in density from 0.24 meters and 0.43 meters up the tank? So let's label a few things. I know that my difference in pressure has to do with the density times gravity times height. So let's label on our picture. My density is 900 kilograms per meter cubed. So that's here. Whenever you're looking for density, you're looking for mass per volume. So look for kilograms per meter cubed. My gravity is always going to be equal to 9.8 meters per second squared on Earth. And my height has to do with the difference in height between these 2 points. So here's my height. So if my first point is 0.24 meters and my second point is 0.43 meters, my difference gives me my height. So pressure equals, I don't know, density is 900 kilograms, and height equals 0.43 minus 0.24. So that's 0.19 meters. And then I just plug everything into my equation. So I'm looking for pressure. P equals, instead of density, I now put 900. Instead of G, I put 9.8. Instead of H, I put 0.19. Since everything is on the same side of my equation, I don't have to do any algebra. I can just plug it in. So 900 times 9.8 times 0.19. And here you go. Don't forget that pressure is in the unit of pascals. You don't want any naked numbers here. You got to put the unit. The next thing you need to know, if you're trying to find the pressure at a specific point, and that is open to the air, you also have to include the force that air has above that point. So for example, here's the equation you're going to use. If I'm trying to find the pressure at any point down here, remember that not only is the water pushing on it, but the air right above it is pushing on it, so you need to know atmospheric pressure in that condition. So let's say we have a boy swimming underwater, and the pressure on his body is 22,663 pascals. How far under the water is he? Air pressure at any time it says at sea level or regular atmospheric pressure, you're going to use 1,103 pascals. That's just standard atmospheric pressure. That can change based on the weather or the altitude, but if it's standard, that's what you want to use. All right, so let's label some things. We know that the pressure on his body is 22,663. We know that air pressure or atmospheric pressure is 1,103. We know that the density of water is 1,000 kilograms per meter cubed. Now you know that from earlier in the notes when we had the coffee problem, I gave you the density of water. That's a really good one to know. 1,000 kilograms per meter cubed is the density of water. You want to know that. Okay, and what we're wanting to know is at what depth is he? So from the point where it turns from air to where he is, what's that height or depth? So we plug into our equation. The pressure he experiences is 22,663, and that's equal to all the pressure air applies on top. So remember, air is pushing down on this water, which then also pushes down on him, plus the change in pressure from where it ended the air to where you are. So density first, so 1,000 times gravity times 9.8 times height. And we left height as h because that's what we want to solve. Notice you have everything except for one variable. So we have to solve for h. H is on the right-hand side, so we need to get rid of everything else over here. You have to keep like terms together. So since all of these are in parentheses together, that's the second step. First, you have to get rid of this 1,103 because it's by itself, and it's being added to the number with h, so you have to subtract 1,103. Those will cancel. But if you do it to the right, you have to do it to the left. So 22,000 minus 22,663 minus 1,103 equals 21,560. Okay, so that's now on the left. We've gotten rid of our first bit on the right, so we still have 1,000 from here times 9.8 times height. So to simplify this, you have to do 1,000 times 9.8. Still the same thing on the left, and now this is 9,800 h. So you have h almost by itself. The only thing you're doing is multiplying it by 9,800. So you have to divide by 9,800. Those will cancel. Do it on the left. So take your calculator and divide 21,560 by 9,800, and you'll get 2.2. Don't forget to put meters because it is height. Best of luck on all the problems you have with pressure and density and fluids, and I'll see you the next time.